between India and Eurasia, there used to be this ocean called Tethys, and this ocean no longer exists. So what happened is, as India started moving north, this entire ocean disappeared, sank inside the earth. We see remnants of that ocean in some parts, in the Mediterranean, but the entire ocean is gone. It was cold, it was dense, so it sank inside the earth's mantle. Now, as this cold, dense material sank, it touched the bottom of the mantle. So as this sudden influx of cold material at the bottom, it kind of stimulated these hot material to rise from the surface of this core. And as this hot material rose, this gravity low started forming in the Indian Ocean.
This is such an unusual problem. Can you tell us a little bit about gravity holes and how you got onto this subject?
So, yeah, I guess the term gravity hole is given by the media. So exactly what it is like? So you have less gravity in that part of the world. So I'm talking about the northern part of the Indian Ocean.
Okay.
So if you look at this, what we call the gravity anomaly map, and you can see it clearly that there is like a almost circular gravity low in the northern part of the Indian Ocean. So the center would be at the tip of the southern end of India. Now, we have known for a long time, why gravity varies on the surface of the Earth, right? It mostly has to do with the shape of the Earth. The more distant you are from the center of the Earth, your gravity will decrease. And the closer you are to the center of the Earth on the surface, the gravity will increase. So since the Earth is flattened, at the poles, you have more gravity, and at the equator, you have less gravity. So that's well understood. Now, when you subtract this shape factor from the observed gravity, you are still left with these high and low gravity values on the surface of the Earth. And what we've set out to find out that why these two values occur. What is the reason behind this high and low gravity values? Now, this is also known that this mostly comes from the density structures. Density heterogeneity is deep inside the Earth. So the Earth structure, you have this outer layer called the crust, and then you have the mantle, and then you have the core. So it's these density structures inside the mantle that produces these low and high gravities, on the surface of the Earth.
So is that like there's shapes deep down in the Earth where there's more dense rock, or, what is it?
Say if you heat a fluid like water, right? When it's boiling, hot water, when you're heating it at the bottom, hot water is light. So it rises at the top, and there it becomes cold, it becomes dense, and it's sinking, right? So we call this convection currents, and we are used to see it any kind of boiling liquid. Now the same kind of convection currents occur inside the Earth, inside the Earth's mantle. But instead of water, what we have is rocks. So believe me or not, rocks inside the Earth are convecting. But because they are rocks, they are not convecting at the same speed as a liquid water will do. It is convecting at a very, very slow rate. So the mantle is getting heated at the bottom from the core, and that hot mantled rock is rising up because it is hot, so it's less dense, so it is rising up. And then at the top, you have these outer layer, that's the crust, which is colder. And at points on the Earth that we call subduction zones, this outer layer of rock sinks inside the mantle because it's cold and it's dense. So these sets up these convection currents within the mantle. So these highs and low gravities that we see when we subtract out the effect of the shape of the Earth is because of these convection currents, these hot and cold density structures inside the Earth's mantle.
When you say they're moving, how fast are they moving?
So they are moving at a rate of a few centimeters to millimeters per year. So it is a very, very, very slow rate. But when you add that up for millions of years, then it becomes a substantial number, right? So because we know that the Earth has not been like this for a very long time. So millions of years ago, you had all the continents together. With time, they split up, and now they are all dispersed in different places. But there will also be a time again, after several million years ago, then the continents will all come together. And all these things that's happening on the surface of the Earth has got to do with what's happening deep inside the mantle. That all has to do with this convection that's going on inside the Earth's mantle. And this convection also affects these gravity values that we see on the surface of the Earth.
Now, why will they come back together?
because it's a cyclic process. We call them a supercontinent cycle. And this has happened several times over the Earth's history, starting 4.5 billion years ago, when we believe that the Earth formed. So you have the supercontinents, which with time they will come together, and then with time again they will split. Now, why they will split? There are many, many hypotheses. So one hypothesis is that you're trapping a lot of heat when you have continents, and so you have this hot material coming from the core, and that basically pushes apart the continents, and the continents split up. And again, with time, they combine, they join. So this process happens again and again and again.
How does the climate crisis, global warming or things like that, how does that impact? Does it impact them coming together?
Things like climate variations, in things like global warming, the anthropogenic climate change, that is happening at a much shorter time scale. But what I'm talking about, is a very, very, very long time scale. So global warming probably doesn't affect this whole supercontinent cycle. But on the other hand, this whole movement of the plates, this convection affects climate. So for example, when you have things that are splitting up, it produces a lot of volcanism. So when you have a lot of volcanism, that releases these greenhouse gases, sulfur dioxide, carbon dioxide, from deep inside the Earth. So you're adding these extra greenhouse gases to the atmosphere, and that's definitely going to affect climate. But not the other way around, because, this is a very, very long time scale, these processes.
We're a sphere. Why isn't the sphere completely flat everywhere? As we move through space, why are there mountains?
The mountains have got to do with what's going on inside the Earth. So what happens, this whole concept of plate tectonics, Earth's crust is broken up into these blocks called plates, and they move around. And that's because of the convection going on inside the Earth's mantle. So the plates are sitting on the top, and as the mantle is moving, the plates on the top are also moving. So when two plates come together, if one plate is heavier than the other, denser than the other, that plate sinks inside the mantle. But sometimes what happens, the two plates have almost equal density. Neither is lighter or denser. So these two plates collide, and you get mountains. So for example, the Himalayas that we see, or even the Andes, that's because of collision between two plates. In the case of the Himalayas, the Indian plate, which was, at one point, hundreds of millions of years ago, the Indian plate was close to Antarctica. It was in the South Pole. And then with time, they split, and India started to move northward, and it collided with the Eurasian plate. And that's how we got the Himalayas. So this is, one of the big reasons you have mountains. So whatever is going on in the Earth has a lot of effect on what we see on the surface, from volcanism to earthquakes to mountains.
There's a theory out there for a long time that there's these differences in gravity. It's not even a theory. We know that there's a different measurement of gravity in this particular area. Now, How do we know that? How does somebody even find that out, that gravity pulls less there?
So these measurements are very accurate. These are mainly done by satellites. So as the satellites are going around the Earth, they measure the value of these acceleration due to gravity. So small changes in the gravity will be recorded by the satellite data. We have instruments that are precise enough that can measure these very, very, very small changes in gravity. So that has been known for quite some time. Even if you subtract out the effect of the Earth's shape, the fact that it's flattened at the poles and bulging at the equator.
And some of your colleagues see this, and you start to think about, well, why could this be? Now, is it like 5 of you are sitting around a table thinking about this problem? Why does this problem grab you and get you interested?
There are some persistent questions in this community, in the geophysics community, that have been not clearly understood. So I talked about these values of low and high gravity over the surface of the Earth. Now, most of these are well explained. We know why the gravity is high at some place and low at some place. But this particular one, and this is the most prominent gravity low on the surface of the Earth. So this particular gravity low was still unexplained. People had different hypotheses, but they still could not explain it fully. So there have been people who have been working on it, trying to explain why this has been around. So this is kind of a persistent question in this community, that why do we have such a low value of gravity at that place?
how would you know? How does it express itself? What's the manifestation of this such that you would even be studying it? How does it affect people or whatever?
The manifestation is that the fact is that since the gravitational pull is less, what happens is the sea surface, the ocean surface, the sea level itself goes down, and it goes down by 100 meters.
That's a lot, right?
Yes, it's a lot. But again, mind you, the 100 meters it's not like an abrupt drop. It kind of becomes in a low over like thousands of kilometers. So it's over a very large area. But still, the lowest point is about 100 meters. So if you're on a ship sailing across this region, your ship will actually go down and then come up. So there is kind of, that's why probably the media called it a hole, which is, not really the scientific term. But yes, there actually the ocean surface goes down. So that's the most, prominent manifestation of this gravity law.
Would you feel it though when it's not like, I mean, the cartoon version, it goes like that, but you don't really feel it, right, when you're on that ship, or do you?
You won't feel it, but again, because again, we are talking about very small values, and again, it's taking place over a very, very large area. So it's not like an abrupt drop.
You and some colleagues decide, well, maybe it has to do with the plumes that are inside the Earth, right? I imagine, at the Institute of Science in Bengaluru, you have a supercomputer. And so, you run a simulation. Like, what's the thought process about how you're going to solve whether this is possibly the answer?
So there are two aspects of it. One is, why is it there today? And once you figure out why is it there today, the second question is, how did it originate there? So why is it there today? We tackled this question a few years ago. So we have another, paper in 2017 where we looked at these density structure inside the Earth. So this is available, there is a branch in geophysics called seismic tomography, which basically gives you pictures of the Earth's interior. When I say pictures, in the sense like how the density varies. And using that, we kind of figured out that why this gravity low is there at this point. Now, what we have done in the most recent study is we tried to take a step back and ask the question, how did it form in the first place, right? How did it originate? So for that, what we did is, so we needed to go back in the past. So we did simulations that started 140 million years ago. So how do we know what happened 140 million years ago? Well, we kind of have an idea what the Earth's surface looked like 140 million years ago. So we could reconstruct back where the plates were. Again, the Earth's surface looked very different. North America was not where it is now. India was not where it is now. And we have these kind of idea about what the configuration of these continents were. And we also kind of can reconstruct how fast these continents or these plates moved with time. So using that, we started a simulation at 140 million years ago, and then with each time step, and we ran those simulations forward in time until the present day. And we saw that, as I was saying, that the Indian plate was in the southern hemisphere close to the Antarctica, and with time it moved northward. Now, between India and Eurasia, there used to be this ocean called Tethys, and this ocean no longer exists. So what happened is, as India started moving north, this entire ocean disappeared, sank inside the earth. We see remnants of that ocean in some parts, in the Mediterranean, but the entire ocean is gone. Okay. So this entire Tethys ocean, it was cold, it was dense, so it sank inside the Earth's mantle. So as this cold, dense material sank inside the Earth's mantle, it touched the bottom of the mantle, right? What we call the core-mantle boundary, the boundary between the core and the mantle. So as this sudden influx of cold material at the bottom, it kind of stimulated these hot material to rise from the surface of this core. And as this hot material rose, this gravity low started forming in the Indian Ocean. So without this Tethys slab sinking inside the mantle, you wouldn't get these hot material rising from the core mantle boundary, and you wouldn't have this GI. So once this ocean disappeared and sank inside, so this cold material stimulated this hot stuff which rose up, and that's when about 30 million years ago this whole gravity law started taking shape.
When you say it happened quickly, how long did it take for the ocean to sink?
Several tens of million years.
Right.
Not very quick.
Yeah, not quickly enough for us, but several tens of million years. Yeah.
Now, when you do that sort of simulation, how do you verify that this is what happened? Is it just that the model actually conforms to all of the existing facts that you can look at?
Yes. So, as I said, we can reconstruct back the speed of the Earth's surface at different time scales. So, we use those to kind of run the convection in the mantle, right? So, how we know a model is right is that we know what the gravity structure is, right? That gravity low or the gravity highs. We know the pattern of that. We also know what the configuration of the plates are like. So, at the present day, if your model is right, it has to give rise to the right kind of gravity measurements on the surface, right? So we ran, it's not just one single model, right? We ran several models. And out of these, only few of these simulations were able to match the present gravity structure. And those were the ones we think, those have to be the right ones, right? There were many others that could not match the present day structure. So the difference were like for all these models, we varied different parameters. And, we kind of wanted to see that what are the parameters that are necessary in order to give rise to this gravity level.
Now, can I ask just a question about, with all of these kind of really studying what's going on, and we don't really know very much, do we, about what goes on down below the surface, right? And so why is your reason for doing this? Like, obviously you're a scientist, and so it's exciting to you, but beyond that, are there other lessons learned? Like, what other things can we be learning from the outcome of the models that could have bigger consequences or ramifications of how we think about our life on Earth?
You're right that we know very little about what's there inside the Earth, right? Because we do not have any way of looking through. So the deepest borehole is 11 kilometers. And the crust, the outer layer, is about 35 to 40 kilometers. And then you have the mantle that goes to 2,900 kilometers. And then you have the core. So the radius of the Earth is 6,371 kilometers, of which we have, direct access for about just 11 kilometers, only one place on Earth. So we then rely on indirect methods to understand what is happening. Over the past several decades, and this is a branch in geophysics called seismology. So basically, whenever you have earthquakes, we use earthquake waves. So whenever you have an earthquake, anywhere on Earth, big or small, there are these waves that are generated by the shaking, by this rupture process. And these waves travel throughout the Earth, throughout the inside of the Earth. And as they travel through the Earth, they collect information about the Earth structure. And then we have instruments we call seismometers. Presently, the Earth is pretty well covered, at least the accessible places, by seismometers. So these instruments collect these seismic waves, and then scientists can analyze those waves and get to know what is inside. And when I say what is inside, they give us some indication of the velocity, or in other words, the density structure of the Earth. So we know where we have cold, dense material and where we have hot, light material. So we do have now, is it 100% accurate? Probably not, because it depends on your coverage, where these earthquakes are, and what's the resolution, the inverse, the methodology that you're using to image those. But we kind of have quite a fair idea about what is going in, what is sinking, and what is coming up. So why does it matter? One thing is definitely about curiosity, and we want to know what's inside, right? The planet that we live on. And even this theory of plate tectonics, the fact that the Earth's surface is moving, right? As far as we know, Earth is the only planet in the solar system that has plate tectonics. So no other planet in the solar system has plate tectonics. So it is very unique to Earth. And sometimes, again, we don't know for sure, but sometimes a lot of scientists are of the opinion that the life on Earth is because of plate tectonics, because you have this recycling of material, right? So what's inside is coming out because of this convection in the mantle. So you have volcanism, so you have these gases that are being released in the atmosphere. So sometimes people are of the opinion that plate tectonics is responsible for life on Earth. Now, we don't still know for sure when plate tectonics started. Again, there are various theories. Some say it started, right at the beginning, 3 billion years ago. Some say, no, it is much more recent. So we still don't have a very clear idea. And I think a lot of these studies are kind of trying to understand why, this plate tectonics even happen and why we have this mantle convection that causes plate tectonics. And this also has an effect on earthquakes, for example, right? So the earthquakes, the surface of the earth, there is a sudden stress buildup and then it ruptures. The earthquakes is happening because one of the reasons is, for example, collision of the plates. Where two plates collide, that's where we have the strongest earthquake. So, for example, the recent Morocco earthquake, right? This is a collision zone. So you have the African plate in a southern part and the Eurasian plate in the north. It's a collisional boundary. So as these two plates, are colliding, you have a subduction zone.
I just assume everything is static, but everything is always moving. I think, is that correct as the way that you're describing it? Nothing just is staying in place. There's constant.
There's nothing static.
Yeah.
Yes. Okay. Earth is very, very dynamic. It's both the surface and the earth internally. It's very dynamic. It's constantly moving, though the rate is very slow, right? I mean, centimeters and millimeters per year. But again, as I said, with thousands or millions of years, if something is moving, that thing adds up.
A different way to think about the earth, though, for me, because I think about the things on top of it growing, but not inside of it. What about you, Jesse?
Well, I hadn't thought about it much, I guess. What does this tell us about the sun or, big bodies like Pluto or, a big giant planet? Does it give us some insight into what's going on in those places?
So the sun is a star, so that it has a very, very different mechanism than planets like Earth.
But isn't that the same convection thing where things are moving up and down inside the sun, or no?
Well, there are convection currents, but then they're very different kinds, right? Because the entire sun is kind of boiling, right? It's like probably 6,000 degrees or even more, right? So that phenomenon is very, very different. But it may give us insight into what's possible in many of the rocky planets. So, for example, many of the space exploration missions that are trying to find habitable planets, some of them are looking for signs of plate tectonics because the hypothesis that probably because of plate tectonics, there is water and there is life on Earth. So I guess in terms of its impact on other planets, this could be the key to finding a habitable planet, maybe.
So you've sort of used this to demonstrate this model. Where does your research go from here?
I think there are many, many questions, again, that are still not answered properly. So, for example, I was talking about these as the India moved northward, there was this entire ocean that sank and disappeared. It's a very unique phenomenon. The Indian plate moved at a very, very fast rate at some point, over a period of 20 million years. It just accelerated. And we don't have any evidence of that anywhere else on Earth. Now, why it did so, again, we don't have a very clear answer. So there are hypotheses, but we still don't know why it happened, So some of these questions are still persistent, and we still do not have a very good idea about why certain things happened. So these are some of the, things that my group basically, we try to address. The relation between what's going on, and this is all related, whatever, as I was saying, whatever we see on the surface, the movement of the plates, the building of mountains, and what is going on inside. So that's what, my research group and I am particularly interested in. It's basically how the surface talks to the Earth's interior, because, both the things are very, very coupled.
And how will you go about untangling that? How will you go about thinking about it? Will you come up with the hypothesis and then try and run it on the supercomputer again?
Yes. So usually, we have a few sets of hypotheses, and then we test them one after another, trying to see which one of those are able to match present day scenarios or even past scenarios which we know, for example, the rate at which the plate moved. So we will have a series of hypotheses, and we will use the supercomputers, the simulations, to understand what actually might have happened.
Well, it's amazing work. It's quite an insight that you found there. Congratulations.
Thank
Now, it wouldn't have anything to do with the Bermuda Triangle, would it?
No, it's a very, very different place.
Yeah.
It's not in the Indian Ocean.
Yeah.
Kind of the idea, the concept of that dip is just so great, even if it is millions of, it's very large.
It's very big. Yeah, it's over a large.
But anyway, thank you so much for joining us, and continue on with your great work that you're doing.
Thank you very much.